Welcome to SS2 Physics, Term 3, Week 6. Nuclear energy is the most concentrated form of energy known. A small amount of nuclear fuel releases enormously more energy than the same mass of chemical fuel. Nuclear fission powers our current nuclear reactors. Nuclear fusion powers the stars including our Sun, and may provide abundant clean energy in the future. By the end of this lesson, you will define mass defect and binding energy, apply Einstein's E equals mc squared, distinguish fission from fusion, explain chain reactions and nuclear reactors, and answer WAEC examination questions on nuclear energy. Let us begin. Einstein's famous equation E equals mc squared, 1905, states that mass and energy are interchangeable. E equals energy, joules, m equals mass, kg, c equals speed of light equals 3 times 10 meter per second. Mass defect, delta m. The mass of a nucleus is always less than the sum of the masses of its constituent protons and neutrons. The difference is called the mass defect. Example, helium, for nucleus, 2 protons plus 2 neutrons. Mass of 2 protons is equal to 2 times 1.00728 equals 2.01456 U. Mass of 2 neutrons is equal to 2 times 1.00867 equals 2.01734 U. Total mass if separate equals 2.01456 plus 2.01734 is equal to 4.03190 U. Actual mass of E for nucleus equals 4.00150 U. Mass defect equals 4.03190, 4.00150 is equal to 0.03040 U. U equals unified atomic mass unit equals 1.66 times 10 to 27 kilograms. 1 U equals 931.5 MeV/C superscript 2. Binding energy, the mass defect, converted to energy using E equals mc squared, gives the binding energy, the energy that would be required to completely separate all the nucleons in the nucleus into individual protons and neutrons. Binding energy equals delta m times c superscript 2. Binding energy per nucleon equals binding energy / number of nucleons, A. The binding energy per nucleon reaches a maximum around iron 56, Fe 56, in the periodic table. This is crucial. Nuclei lighter than Fe 56 release energy by fusion, joining together, because the product has higher binding energy per nucleon. Nuclei heavier than Fe 56 release energy by fission, splitting apart, because the products have higher binding energy per nucleon. This explains why the Sun fuses hydrogen to helium, releasing energy, and why nuclear reactors split uranium, also releasing energy. Nuclear fission is the splitting of a heavy nucleus into 2 smaller nuclei, fission fragments, plus energy and neutrons. Most commonly used for energy production, uranium-235 fission. When a slow, thermal, neutron is absorbed by U-235, 235-92, U plus 1-0 and 236-92, U, unstable compound nucleus, fission products plus 2 or 3 neutrons plus energy. Example reaction, 235-92, U plus 1-0 and 141-56, Bo plus 92-36, Ka plus 3 times 1-0 and plus energy, approximately 200 MeV per fission. Energy released per fission, approximately 200 MeV equals 3.2 times 10 to 11 J, compared to burning coal, about 3.3 times 10 to 19 J per reaction, chemical bond. Nuclear fission releases about 10 million times more energy per reaction than chemical reactions. Chain reaction, each fission releases 2 to 3 neutrons. These neutrons can each trigger another fission. In an uncontrolled chain reaction, each generation doubles or triples the number of fissions. Exponential increase in energy release explosion. This is the principle of the atomic bomb. Critical mass, the minimum mass of fissile material, AgU 235, required to sustain a chain reaction. Below critical mass, too many neutrons escape without causing fission, chain reaction dies out. Above critical mass, chain reaction grows exponentially. In a nuclear reactor, chain reaction is controlled. Control rods, boron or cadmium, absorb excess neutrons, keeping the reaction at a steady rate. Exactly 1 neutron per fission triggers 1 more fission on average. Moderator, water, heavy water, or graphite, slows down fast neutrons to thermal energies at which fission probability is highest. Nuclear reactor components, fuel, enriched uranium 3 to 5% U-235 in U-238, natural uranium is only 0.7% U-235. Moderator, slows neutrons to thermal energies, water, heavy water, or graphite. Control rods, absorb neutrons to control rate, boron, cadmium, hafnium, inserted to slow/stop reaction, withdrawn to speed up. Coolant, carries heat away from the reactor core to generate steam for turbines, water, CO2, liquid sodium. Pressure vessel, contains the core. Shielding, thick concrete and lead walls protect workers and the environment from radiation. Steam generator, heat from coolant is transferred to water to make steam, steam drives turbines, turbines drive generators that produce electricity. Nuclear fusion, two light nuclei join together to form a heavier nucleus, releasing energy. Most promising reaction for future energy production, deuterium plus tritium helium, 4 plus neutron plus energy. 2-1 H plus 3-1 H 4-2 He plus 1-0 M plus 17.6 MeV. Conditions for fusion, extremely high temperature, 100 million Kelvin, to overcome electrostatic repulsion between nuclei, plasma. This is what happens in the Sun. Solar core temperature is about 15 million K, which is sufficient for proton-proton fusion. Advantages of fusion, abundant fuel, deuterium from seawater, tritium produced from lithium, no long-lived radioactive waste, product is E4 and a neutron, tritium has T1/2 equals 12 years, no risk of runaway chain reaction. Challenges, achieving and containing 100 million degree plasma is extremely difficult, no commercially viable fusion reactor yet exists, JET, ITER, under construction. Comparison, fission, currently used in power stations, proven technology, produces radioactive waste, risk of meltdown, e.g. Chernobyl 1986, Fukushima 2011. Fusion, not yet commercial, cleaner, more abundant fuel, theoretically safer. Worked example 1, calculate the binding energy of a nucleus if its mass defect is 0.03040 U, 1 U equals 1.66054 times 10 to 27 kilograms, C equals 3 times 10 meter per second. Delta M equals 0.03040 times 1.66054 times 10 minus 27 is equal to 5.048 times 10 to 29 kilograms. E equals delta M times C superscript 2 equals 5.048 times 10 to 29 times 3 times 10 superscript 2 equals 5.048 times 10 to 29 times 9 times 10 superscript 1 equals 4.54 times 10 to 12 J equals 28.4 MeV. Using 1 U equals 931.5 MeV, E is equal to 0.03040 times 931.5 equals 28.3 MeV, consistent. Worked example 2, in a fission reaction, mass defect is 3.1 times 10 to 28 kilograms. Calculate energy released. E equals mc squared equals 3.1 times 10 to 28 times 3 times 10 superscript 2 equals 3.1 times 10 to 28 times 9 times 10 superscript 1 equals 2.79 times 10 to 11 J. This is approximately 174 MeV, consistent with the order of magnitude for nuclear fission. WAEC note, E equals mc squared calculations are often tested. Always show the formula, substitute with correct units, and give the answer in joules. Some questions give data in atomic mass units, U, convert to kg fast, or use 1 U equals 931.5 MeV directly. Key points, E equals mc squared, Einstein's mass energy equivalence mass and energy are interchangeable. Mass defect, actual mass of nucleus is less than sum of masses of constituent nucleons. Binding energy equals mass defect times C superscript 2, energy needed to completely separate the nucleus. Higher binding energy per nucleon equals more stable. Fe 56 has maximum binding energy per nucleon. Fission, heavy nucleus, U 235, splits into smaller nuclei plus neutrons plus energy, almost equals 200 MeV per fission. Chain reaction, each fission releases neutrons which trigger more fissions, controlled in reactors with control rods, uncontrolled equals atomic bomb. Nuclear reactor, fuel, enriched U 235, plus moderator, slow neutrons, plus control rods, absorb neutrons, plus coolant, remove heat, steam turbines, electricity. Fusion, light nuclei, D plus T, combine to form heavier nucleus plus energy, 17.6 MeV for D plus T, requires 100 million K, powers the sun, potential future clean energy source. Fission versus fusion, fission, current technology, radioactive waste, fusion, cleaner, more abundant fuel, technically very difficult.